Hi, this is Ralf Lämmel and I would like to talk about monads today. As you probably know, monads correspond to one of the supernatural powers of Haskell and functional programming. So technically, monads are abstract data type constructors, and conceptually they are supposed to help you organizing the computations in your program. And in particular, they should help you with side effects, resources, runtime optimization. There are many good monad tutorials out there, and also, monads, this is such a huge topic. It's hard to come up actually with a plan for a lecture. So what I decided is I would limit myself to actually Phil Wadler's seminal paper, The Essence of Functional Programming, where he introduced or discovered monads for functional programming purposes back in 1992. So this is a POPL paper. POPL is the major programming conference, and I'm basically picking examples and discussion points from his paper. So I'm not complete, so therefore I call it the quick essence of functional programming. So the paper uses interpreters to motivate monads, and so here we go. So we use some abstract syntax for lambda calculus. Just for clarity, here's also the same term shown in Haskell syntax. So basically this is a term that applies a lambda abstraction for the double function to this term here, which essentially evaluates to 21. Right, so this is the interpreter function, this is the term, there's also the empty environment, so we apply it, and so it's 42. So the point here is we will again, a little bit like last time, evolve this interpreter and add some computational facets to it. And eventually we will use monads to deal with those computational facets. Okay? Just for completeness sake, here's the list of syntactic and semantic domains. No surprise, I guess. There are these kinds of terms, variables, integer, constants, addition, lambda abstraction, and function application. And this is our value domain. There's a case for partiality, if you like, wrong, and there's a case for numbers, and a case for functions. So environments this time are modeled as lists of name-value pairs, and this is the signature of the interpreter function. So we take a term, we take an environment, we return a value. So with regard to this monad theme today, you should basically watch this position here, in the sense that this is where we will enrich this function so that we incorporate computational facets, such as producing output or error messages. Okay? And these are all the functions of the interpreter, essentially the interpreter function plus some helper functions. I don't think we have to look at this, very closely at this point. There shouldn't be any surprise. It's just usual case discrimination and recursion, and look up for the environment here. Just as a list processing function which goes over the list to find the binding. The add function here is just a helper for the interpretation of add, in the sense that it makes sure that the two numbers are real numbers rather than other values to be added. Likewise, here we can only apply a function and not a number in this position. So that's it. So if you want to have an exercise to familiarize you a little bit with this interpreter, here is one. What you could do is you could basically revise this interpreter to replace the kind of environments that we have here, which are based on lists of name-value pairs, to use instead environments that are functions, as we did last time. So that's probably useful. Okay? Okay, so now let's try to extend this interpreter. And monads will sort of suggest themselves eventually. So for example, we might want to produce output along interpretation. For example, you might want to perform tracing or logging, and to this end you need to synthesize output. So it's not too hard to see how the signature of the interpreter function has to change, right? So basically, since we now need output in addition to the value, well, we just return a pair here. Alright, so that's easy enough. Or another scenario, suppose you want to produce proper error messages. I mean, currently we have this case wrong in the value domain, so at least we can signal some problems. But if you want to return proper error messages, you might need something like this. So you either return a string or a value. So string being the error message. And here's yet another scenario. Suppose you want to deal with some mutable data structure in your program, in your interpreter. And so this means you have to kind of set up the scheme of state transformation, right? So which means like your interpreter function receives an initial state and it returns a value as before, but it also returns the state resulting from the execution or interpretation of that term. Okay, so the point here is, okay, we can see how we need to elaborate the function signature for interpretation, but that's of course not enough. We also need to sort of rewrite the actual interpreter function to, you know, satisfy this type. So, you know, let's just do this for one case. Let's consider the state transformation case here, you know, for mutable data, for example. I have just done the exercise of rewriting the interpreter function. Now it's probably hard for you to see what changed, so here's a little animation. So you see all the added spots and affected spots, right? So you can basically see that all the equations received an additional argument for the initial state, and that on all the right hand sides there is pair construction going on, because we always have to return a value and the resulting state, and there's this sort of, you know, sequential threading going on here in the sense that we have to line up these subterm interpretations so that we kind of you know, computed the immediate state as one, which we then pass in here, and so on. So it's pretty complicated, no? I mean, and it's actually, you look at it and you don't really see, you know, for sure that this is, you know, proper state transformation. It sort of obfuscates the original interpreter, and, you know, you also have no code level reuse, right? You have basically rewritten the entire program and you're not even sure what it means. Anyway, so here's a little exercise. So you could also do the same kind of revision for another computational facet, such as you know, the output that we mentioned on the previous slide. The program that we have seen was rather ugly. So what could we do? I mean, one thing is we could just give up on using Haskell and use a, you know, impure programming language instead, which, for example, natively provides us with state mutable variables. Or we could instead use a monad. So if you want to use a monad in our interpreter, we have to parameterize the program in a type constructor for computations. That's step number one of going monadic. Okay, you see basically in all these function types here, we use this uppercase M, the placeholder for the monad type constructor, in the result type, right? So this means that all these guys can participate eventually in the computational facets such as state transformation that we have in mind. So you see we have the auxiliary functions here, the interpreter function, and we also have patched the function type case of the value domain, okay? So here's a few examples of how we can instantiate M then. Well, in the trivial case, we can actually apply the identity type constructor, which means that we wouldn't add any computational facet to the interpreter. Or we could define it like this, which would mean we would really add output potential here. And then we can also set up the type constructor to use that function type here, so that would model state transformation. Okay? So as far as terminology is concerned, you know, A is always kind of about the values in our program or the data in our program, whereas MA is about the computations in our program. And I should also mention that in actual Haskell programming then we often prefer M to be an abstract data type constructor so that we properly encapsulate the computational facet. So step number 2 is that we actually make our program fit to deal with this updated type of functions, right? So we need to use computations in our program, and most importantly, we need to set up chains of computations. So let's start from the baseline interpreter. So we are only looking at one case here, at the case for addition, and let's try to understand how this case evolves into monadic style. Okay. So one thing to notice here is that we use, nested function application. So what you need to do in order to become monadic style, you need to sort of sequentialize the program. So what you do is, in this case, you first interpret the left operand and the right operand, and then you apply addition. Right? So this transformation by itself doesn't change the type or the semantics of the baseline interpreter. It just kind of illustrates kind of how we could think of interpretation to proceed in sequential steps. But now we can kind of replace those lets by the monadic bind operator. This is the bind operator. So basically now we really set up a chain of computations. So, this is the first computation, namely to interpret the left operand, and then the idea is that we bind the value that comes out of this computation to A, and then this is the next computation, and again there's a value that comes out of it and we bind it to B, and then we perform addition as the last piece of computation in our chain. And there's also convenience notation supported by Haskell. You can also write it down like this. It's the so-called do notation. So here are the 3 ingredients of a monad. We have seen a type constructor, we see the bind operator, and there's also a return operator. And its purpose is probably obvious from its type, so we can take a value and turn it into a presumably trivial computation. Okay, and so we also see the type of bind now, from which it is obvious that it's meant to compose computations. So we have a computation here, and then a function that takes a value of that kind and then proceeds as a computation. So we can sequentially compose computations. This is the identity monad that we started already on the previous slide. So we use the identity type constructor. We use the identity function for return, so we construct computations from values with the identity function. And the bind operator is basically the function application. So this is the most trivial monad there is. And if we use that monad with our monadic style interpreter, we essentially get back the same interpreter that we started with. So we can still compute 42. Here are all the gory details. This is the interpreter function of our interpreter now in monadic style. So you see I highlighted all the places where we construct computations and where we chain up computations. So this is the equation that we looked at before, and you see actually that the case for function application looks very similar, just because we again have like 2 sub-expressions, subterms that we need to interpret and that give rise to computations that we need to chain up. So, right, and so this one here we should look at a little bit more. So to understand the role of return, we have this constant here and we want to return a value. But we can't return just a value, because by the type of the function we have to return a computation. So we need to go from a value to a computation, and this is what return does. Okay? Here are the auxiliary functions. They also change a little bit, because we again have to construct computations here and there because of those types that now return computations. Perhaps an interesting little riddle for you. There is no bind operator in this set of functions here. So why is that? It's not entirely trivial to come up with a convincing explanation. So now let's revise our monadic style interpreter to actually incorporate some computational facets. Let's start with error messages. So I kind of compare the baseline behavior with the expected behavior. So this is like the term that we use. It has an error insofar that we try to apply a constant to constant. Right? So if we run this term on the baseline interpreter, well, it just says wrong. Okay, so it signals a problem, but we would like to have such an error message instead. So this is the revision we want to achieve. That the error message says, hey, this should be a function, and what should be the function? Well, the first argument here, which is 1, right? Okay, so in order to achieve that behavior, we need the error monad. The error monad uses a type constructor with two cases, a success case and an error case. Or we could also use the either type constructor, but I stick to the code of Phil Wadler's paper here. So how do we construct a trivial computation from a value? Well, we just commit to the success case. How do we chain up computations? Let's see. So if we have a successful computation here, then we use function application, right? If we have an error case here in front, well, then we just propagate the error. Very easy. And then with every specific monad, we usually need operators to deal with the computational facet at hand. Now, in the case of the error monad, we need an operator fail so that we can actually construct an error message. Okay? So given a string, we commit to the error case, and type-wise, we construct a computation. Now we still need to patch the interpreter to make use of error messages. So this is an important insight here. Like, it's usually not enough to just instantiate a monadic style program with a specific monad. Often we also have to replace some tiny parts of the program to make use of the monad. So in this case, you know, we have this kind of baseline definition of apply, but we want to propagate error messages here when, you know, this case happens. So we have to patch the apply function and to rather invoke fail here. So I call this a selective code replacement as opposed to a global rewrite. So it's still, you know, better to have a little bit of selective code replacement rather than, you know, no code reuse at all. So there's one interesting detail going on here. We basically, when we run the interpreter, we rely on show to, you know, sort of print the result of interpretation. Now, however, since everything is a computation, we are essentially printing computations. Another way to think of show as we run it in the interpreter session is that it gets us out of the monad. So basically, you know, if we have a, you know, computation like this, what show does is it converts it into a string. So given a computation, we get a string from it. So, you know, with every monad we have this problem that we, at some point, we need to run the computations that we have composed with bind and otherwise. So, you know, currently what we do in order to run the computations is to actually show the result. Okay? So the next revision is due. We would like to read the reduction count in our interpreter. It's a fancy extension here. So by reduction count we mean the number of function applications that were carried out, including additions. So let's look at a demo here. So you see, we set up a little convenience function here to interpret a term and to show the result. And now we actually apply this interpreter function to this term here, add 21 to 21. And this is now, with the revision that we have in mind, this is how it should look like, the result. So we would want to know, okay, the value, the result of the computation is of course 42. But by the way, the reduction count is 1, because there was one addition here. Okay? So another example, so we actually want to add a little bit more here. So, you know, we set up a constant 0, and now we carry out this computation. So we add 0 to 0, and then we add that one to count. Count is our new construct for reading the reduction count within the interpreted program. So what happens here is that we get the result 1. Why is that? So we add 0 to 0 is 0, and then we add 0 to the current reduction count. At that point, when we read the reduction count, one addition, namely this one, has already been completed. Therefore, the reduction count reads as 1 and the whole expression evaluates to 1. However, now we are also completing that second addition, so in the end the reduction count is 2. So how do we get this behavior? Well, we're going to use the state monad to carry around the reduction count. So this is the state monad. Given this value type, we construct the function type. State is mapped to a value and to a new state. So since we want to count reductions, we instantiate the state type to be int. So now, how do we construct trivial computations from a value? Return A. Well, we just have to construct a trivial state transformer. What is this trivial state transformer? That's one that totally preserves the state. Given a state and given a value, return that value and the same state. How do we chain up computations that are state transformers? Well, we basically have to set up threading for the state, right? So we take the initial state here, we apply the first computation to that initial state, we get an intermediate state and a value, we pass on the value and the intermediate state to the second computation, and so we get a final state and a final value. Now with the state monad, or with the kind of reduction counting instance of it, we need these two guys here. We need a tick operator that basically increases the reduction count. So you see, this is this kind of guy. It takes a state, doesn't return any useful value, but it returns the increased reduction count. And then we also need to fetch the state, say the reduction count, for the extra construct count that we have seen. So we can read the reduction count. So, given a state, we return the state, which is an int in our case, as value here, and we preserve the state. So again, also in this case, we can think of using show as a way of getting out of the monad. So when we want to show that sort of computation, well, what we have to do is we have to come up with an initial state. So in our case, this is the reduction count 0, so we can run the whole thing, and you see we get a value and a final state, and then we can set up that sort of showing behavior that we also saw in the session, right? Okay, so now this is what we need to do beyond providing this monad instance. That is, we need to perform a data extension and again selective code replacement. So this is interesting. On one hand, because we have a new construct in our interpreted language, we have to perform this interpreter extension. On the other hand, we also have to rewrite the add and the apply function, because these guys need to affect the reduction count, right? So more in detail, we add this data variant here for the new construct. We add an interpretation for it. Basically, we read the reduction count, we bind it in this chain here to I, we return I, okay? And then, how do we rewrite the add and the apply function? Well, we basically do the same business as before, so we check that these are numbers or that this is a function, and then do application or do addition, but before we return the result, we perform a tick to increase the reduction count. Okay, another revision. Now let's try to produce output So we envision such an additional construct here out, so that we can, whenever we construct a term, we can basically wrap up subterms to mean that we want to see the result of that subterm in the output, right? So if we compute 42 in this complicated way, well, then we also want to see 41 for this subterm and 1 for this subterm in the output. So we use the writer monad to this end. The writer monad basically couples up the value with the string for the output. How do we construct a trivial computation? Well, we take the value, return it, and pair it with the empty string, say the empty output. How do we chain up computations? Well, we first run the first computation, we get some output R and a value. The value goes into the second computation K, and that one produces some value and some output. So we combine the two pieces of output here through concatenation and return the value from the second computation. And then we need a specific operation here. Say we need to be able to produce output. Okay? So say we take a value here. That guy only has the side effect of producing output, so therefore there's no interesting result here. So we make this clear in the type and in how we define it. But we, produce some output here. And then this is how we need to extend the interpreter. This time, just the data extension is sufficient. So we don't need to replace any code. So we just have to add this data variant for the out form of term, and we have to add this equation hence. So we basically first compute the argument of out. So we bind the resulting value to A. Then we invoke our special operation tell to produce output for A. And then we return A as if nothing had happened. So you see kind of underneath we have the side effect here, but we return the value of the interpretation of the subterm. So this is cool, we can have all kinds of revisions like this. Here's another one. We want to add non-determinism to our language. So we can form terms like this, which means either behave like this or like that. So now in the interpreter we basically want to compute all possible results. So the result of interpreting that term would be 2 and 1. Now if we apply the double function to all possible arguments here, we also get a list of results, namely 4 and 2, right? So we need a list monad here to model the fact that we may have multiple values as results, right? So we use the list monad here, and how do we construct a trivial computation? Well, we just construct a singleton list, so one value, a list with one value. How do we chain up computations? Well, we have to construct all combinations here in a sense. So we take this M here, which could be a list, so we use it as a generator in this list comprehension. So we get our hands on all possible values in this list. So we apply K to all these possible A's, and again we might get many B's like this, right? Okay, and then these are the two specific operations that we need for this monad here. Namely, we want to be able to express that there might be a computation that actually produces no result whatsoever. And we also want to take, two computations, MA, and construct a computation in the sense that we combine all the all the possible results here. Okay? Now, this is how we have to actually revise the interpreter other than, instantiating the monad. Well, we again don't need any selective code replacement here, it's just the data extension, so this is a nice case again. So we add two constructs, so we have seen the amp construct for saying, either this or that. And there's also the fail construct when we want to say, this computation, this term shouldn't return any result. Okay, and then there are two equations, fail is mapped to the M0 operator, and amp is mapped to the M plus operator. So we really say, you know, take all these results here and all these results here and just, you know, concatenate them. Alright? It is time to set up a type class for monads. You know, we just have this type class monad. We are parameterized in the type constructor for the monad, and then we have the two operators bind and return. So I haven't used this type class so far because I didn't want to give the impression that monads are necessarily tied to type classes, and in fact Phil Wadler's paper also avoids type classes in the presentation. Anyway, so it makes sense, of course, and there's one interesting bit about this type class, namely that this is actually not really just a type parameter, it is really a type constructor parameter. You know, this is interesting if you compare this with like generics in mainstream programming languages. And another interesting bit should be mentioned about the type class, or let's say about the operators bind and return, namely due to the formal background of the notion of monad, these operators should satisfy some laws, and actually these laws are not just there for formal you know, justification, but they are immediately useful when you do reasoning about monadic style programs, which is also illustrated in Phil Wadler's paper, but I don't do it here. So what are these laws? It's basically that return is algebraically the left unit of bind and also the right unit of bind, and then chaining, say bind, is associative. Yeah, so let's just look at the first one. For example, what you have here is that, you know, if you have a value which you trivially promote to a computation, and then you chain it up with f, while you don't have to go through this computation here, you can just apply f right away to the value. Okay, now with this type class in place, we may want to refactor our program a little bit more, in the sense that so far we have used this uppercase placeholder here, and this is sort of an implicit parameter to our program, in the sense that only once we have a definition for m, you know, our program is complete. This is a little bit strange, you know, when you think about separate compilation. So what we might want to do is, now that we have also the type class monad, is we can sort of make that parameter explicit and thereby achieve true flexibility. And also we can then compile this function without actually committing to any particular monad. Right, so what we do is we kind of start using this type parameter here, m, well actually type constructor parameter, and we also constrain it up here to be a monad based on our new monad class, and then you actually have to put that type class constraint here simply because we are going to use bind and return in the definition of interpret, and only, you know, by means of this constraint bind and return get into scope. But to be honest, that doesn't work yet, in the sense that, please remember that value also had one case in there that was talking about functions, and those functions also had a monadic result type, so actually value also needs to receive the monad parameter now, and because environments build on top of values, you know, the environment type also needs to receive the parameter m now. Anyway, so this is now our preferred function signature for the baseline interpreter, in the sense that it's really explicitly parametric in the monad that we are going to use. So now I want to show you a few instances of the monad class, in a way just to have another set of monads that we can use now in our programs. And so these kind of instances, they actually live in the Haskell libraries. So for example, this is the identity monad. So you see we just set up a new type identity, and as you see, essentially it just wraps in A. So it's really also kind of a type level identity function. And you see how this is kind of the terminology that's used in the libraries. You know, in order to sort of get out of the monad, we usually have sort of run functions here. Yeah, you see. So this is the instance. This is how we instantiate the monad class for the identity monad. You see, return just constructs this wrapped value, and when we bind, well, we just unwrap, you know, the argument computation and pass it on to k. So next monad, the maybe monad. We actually didn't encounter it today, but if you remember the last lecture, we used it for dealing with partiality in the interpreter back then. Okay, so we use the maybe type constructor here to instantiate the monad type class. And well, how do we construct a trivial computation? Well, we use the just constructor of maybe. And then how do we bind? How do we chain up computations? Well, for the successful computation in front, we just use function application, and otherwise we propagate nothing. So this is very similar to what we have seen for the arrow monad, right? And actually now we can reveal that there's another member in the monad type class. It's called fail, and you know, it basically allows us to model failing computations in some generalized sense. So we will have to see what sort of the default should be, or what the definition should be. Let's say, for example, for fail in the case of the identity monad. Okay, so let's then reveal indeed the type class monad in full. Yes, so we have return, as we have discussed, we have bind, and here's actually another member we haven't discussed at all. This is the kind of you know, specialized bind where we don't care about the intermediate result here, right? We just throw it away. And you see it's defined like that. We just, you know, catch it with a lambda, but we don't use it. And here's fail. So given a string, construct a computation, and here's the default. So that default also applies for the identity monad, for example. So this is a kind of low-level Haskell prelude function, which says, you know, just terminate execution with this string. So this default is not very appropriate because it really takes down our program, whereas this definition for the maybe monad is very appropriate because it basically means that we really construct a value in the Haskell sense that models unsuccessful computation. Well, and there is also the arrow monad indeed. So we use the type constructor either this time. And you see we sort of pre-instantiate the first argument of the type constructor to serve for the error messages. Rather than committing to string here, we are a little bit more parametric here. We assume that different kinds of types may serve as errors or error messages or exceptions, right? And then, well, return again, we just commit to the successful case, which is on the right this time. And you know, if we have unsuccessful computations, let's say errors, well, then we just propagate them. Otherwise, we fall back to function application. And it's also clear how we implement fail. Well, we commit to the error case. And here you see how this extra type class for error types works. So in particular, strings are also suitable errors. Okay, I should mention that there's actually a more sophisticated type class called monad error, which is a subclass of monad that allows you not just to sort of throw errors or exceptions, while there's also an extra member then to catch errors, very much like you are used to in terms of exception handling of mainstream programming languages. Speaking of subclasses of type class monad, here are a few more indications. So I'm not going to show you instances here for everything. So just so that you know, there's also a subclass monad state, you know, for state transformation. As you see, it's a subclass of monad, and as you see, it has like two type parameters here, one for the state type and one for the actual, you know, state monad type constructor. So you see, we consider these two operations to be fundamental to state monads. There's a sort of a get operator, you know, that we can sort of query the state, so therefore the result type here is S. And there's also a put operator, so given the state, we can actually, you know, affect the state, assign the state. And, you know, that sort of computation doesn't produce anything useful, it's really just a side effect. And then here there's another class, the monad plus class, and you see we have seen something like this before. You know, this is the kind of monad with addition, with a unit and with addition. So for example, the list constructor instantiates monad plus, and you remember we have used that instance effectively when we were dealing with non-determinism. And I should also mention that actually the maybe monad is actually also a monad with addition. You know, this means like when you use m plus on a maybe computation, well then you can sort of recover from failure. Okay? So all the interpreter revisions that we have discussed so far dealt with one computational facet at a time. That made things a little bit simpler than they are in general, so let's study a revision then where we combine computational facets. So we want to do this kind of interpreter here where we have error messages as before, but in addition we want to have position information. So we think of an annotation kind of term like add42 here that allows us to incorporate line number information into the terms, which means like in this case, well, this part of the term here started in line 42. So in case an error occurs during the interpretation of that subterm here, we want to see that line number as we do down here. Because we try to apply a constant to a constant, which is an error, so we get to see the line number over here. Okay, so let's see how we actually implement that revision. So we start with a naive model here. So we don't yet want to use monads, so rather we want to understand that interpreter with, you know, just with that straight function signature here. And so you see we actually designate an application of the either type constructor so that we can deal with error messages. And that's a little bit like what we did before with error messages. Yeah, so we could use the error monad here, right? But then we also need to propagate the line number information. So we use that part here. And we haven't talked about the reader monad yet, but yes, so that kind of propagation of data would be modeled typically with the reader monad. So the reader monad is for propagation of information down into computations, whereas the writer monad is for, you know, accumulation of information from computations. Okay, so we will have to understand how the reader monad exactly looks like, but the point here is there is actually no easy and general way of taking like two monads, like the error monad and the reader monad, and just compose them. Instead we have to apply a transformational technique where we sort of transform a given monad to incorporate an additional computational facet so that we get a richer monad in a sense. Okay, so that's the interesting bit that we want to discuss here. So let's start with the reader monad then. As you see, we again designate a subclass of monad, the monad reader class. And there are two type parameters here, you know, one for the monad type constructor itself and another one for the information to be propagated. Okay, so we will look at these guys in a second. These are the specific operations of a reader monad, but let's just understand, you know, how the reader monad works. And so you see we actually use the function type constructor where we instantiate the first position, say the argument position of the function type constructor to the type of information that we want to read. And then how do we construct a trivial computation? Well, we just don't look at the information that we propagate, which we achieve with the const here. And how do we chain up computations that, you know, involve propagation of information? Well, we basically receive the information up here and then we propagate it to f, the first computation, and also to k. Okay? So this is how you see how we propagate information. And now let's look again at these guys here. So the two specific operations of a reader monad is that we can, of course, ask for the information that is being propagated, and we can locally transform it or override it, you know, for the scope of one computation. So we can't change it as in the state monad. We can only locally, for the given computation, change it. Okay, and now you see how this works. So here's also the instance for, you know, the function type constructor again. So, well, you know, if we ask for the information, well, then we just, you know, catch it and sort of return it as a value, right? And if you want to locally change the propagated information, well, we just, you know, take the information, we change it with f, and we, you know, feed it into the computation m. Okay. So now, monad transformation. So, you know, what we essentially want to do is, remember, we want to enrich, let's say, the arrow monad to also perform propagation. So, what we need here is, we need the monad transformer for reading. So we use this eventually abstract data type constructor reader t for transformer the t, and it's parameterized like a monad type constructor in A, you know, the value type, and now it's also parameterized in a monad m. So this is how you see that we are going to transform a monad, and because we're dealing with reading here, it's also parameterized in the type for the information that we propagate. Okay? So now I'm not going to show you all the details because it's getting a little bit complicated, but you see that we essentially instantiate the monad type class here with the reader t type, and one of the constraints is that the argument m indeed is already a monad. So you see how we really transform monad m into a richer monad, you know, by the virtue of that instance here. Okay, so I'm not going to show you this code, but it's essentially kind of a lifting code, you know, that generalizes the underlying return, bind and fail operations and adding bits related to the reader monad. Okay, and of course we also instantiate the monad reader type class here because, you know, by taking a monad m and by applying reader t to it, we also get a reader monad. So now we can actually compose or, you know, transformationally assemble our monad that we need for error messages with position information. So I just show you a little bit more code here so that you understand how this is actually done with Haskell libraries. So you're going to import a few modules here. So you need the identity monad, you need the arrow monad or the arrow monad transformer. You also need the reader monad or the reader monad transformer. And then you assemble your problem specific monad here really by, you know, type level transformation. So you see, you start from the identity monad and then you apply the monad transformer for the arrow monad to it, and then yet again you apply the reader monad transformer to that intermediate result. So you see how you compose together your final monad that deals with error messages and positions. So, you know, the essential operation that you need is that you can throw an error message with position information included. So you see, you essentially ask for the position information, so you exploit the fact that this is a reader monad, and you throw the error message using fail, and you use the the interesting fail here that really uses the either type constructor of the error monad. Okay? And here's then the code that carries out the data extension and selective code replacement. So you see, we need to provide a new data variant for the annotation kind of term here. We interpret that new form of term by locally overriding the information of the reader monad. So you see, we actually ignore what's the current annotation. We just set up the new annotation, and then we dive into the subterm t here. Okay, and then for example, when we do function application, for the case that we don't have a suitable value at hand, we throw an error message. And so we say, okay, this should be a function. And what should be a function? Well, this guy here should be a function, but it isn't. And then because of how throw error message is defined, it also adds position information. And finally, here you see how we sort of test the whole interpreter. So this is basically the way how we see how we get out of this, layered monad. So we don't use show anymore. We rather use these run functions, which essentially unwrap those abstract data type constructors, right? So we basically start here, we run the interpreter, and we have to give it some initial position information. Here we go. And then we sort of unwrap it, so we get back something of the type for the error monad, which we unwrap here. And then we also unwrap the identity type constructor due to the use of the identity monad. So we are at the end of our technical development today, and so I want to close with a riddle. Basically, I ask you to try the scenario of error messages with position information by means of your own handmade monad. So the idea here is, well, if you use the monad transformer library, it doesn't really help you very much to understand monads, so perhaps you should define your own non-trivial monad at least once. So yeah, so you would kind of designate one type constructor to cover both, like error messages and position information, and you would instantiate a monad type class as well as the monad reader type class. Okay, and then the final thing is for the reading pointers. I want to start by saying that I haven't covered everything of Philip Walker's paper. So he's also showing you call by name interpretation. I only dealt with call by value. And then he's also spending quite some time on continuations, continuation parsing style, and how it relates to monads. Very interesting topic. My code distribution covers it, but it was too much for today. And finally, he also goes into equational reasoning for interpreters and for programs in monadic style, and he shows how the monad laws help you there. Well, and then here's a few references that kind of cover a good part of the monad story, at least in Haskell. Well, that's actually not a Haskell reference. So David Espinosa back in 1995 had a thesis where he studied the monad composition and transformation problem. And Labra and Gallo in 2001, they had a nice paper on basically combining the discussion of monadic style and expression problem in some sense. Mark B. Jones in 1993, he basically designed more or less the kind of monad and monad transformation libraries that we are still using today. And then Pete and Jones, this is a nice tutorial where he discusses all kinds of monads, and he also goes into issues of operational semantics and performance and realistic implementation. And then there's also the book here, Real World Haskell, if you really want to do some Haskell programming with the monad libraries. There's good stuff in here. And that's it for today. So thanks a lot, and hope to see you soon again.